Hello students, welcome to mathematics class. So in the last video we have discussed the introduction to the singularities of a function, which are zeros and poles, right, and also the theorems on those singularities. And now let us start with the examples on finding the poles and zeros of the given function. So now the first question is, find the poles of the following function. Whenever the question is to find the poles, we need to equate the denominator to 0, because pole means at which the function is not differentiable. So the function is not differentiable in the sense the function is not defined at those points. So therefore for that we need to equate the denominator of the given function to 0. And if we want to find the poles of the zeros of the function given, we need to equate the numerator to 0 for finding the zeros. Now here the question is to find the poles of the function, and the given function is f of z equal to e power z divided by z square plus 4. So therefore here the poles of the function, the poles of the function are given by z square plus 4 equal to 0. So by solving this we can find the pole. So here to find the pole we need to find the value of z. So it is the quadratic equation. So therefore here z square equal to minus 4, then z equal to plus or minus square root of minus 4, which is equal to plus or minus 2i. Then it implies that z equal to 2i and z equal to minus 2i are the poles. And here we know that the order of this denominator, means power of this denominator, is equal to 1 whenever the power of the denominator is equal to 1 and the given values of z will be simple poles. So therefore here z equal to 2i and minus 2i are simple poles. Simple pole means poles of order 1 are called as simple poles. So therefore this is the way to find the poles of the function given. And let us consider the next function, f of z equal to tan z. Here the denominator is not given and the denominator of this function is equal to 1. So now try to write this function as a ratio of functions. So therefore which is equal to sin z divided by cos z, that is equal to tan z. Then to get the poles we need to equate denominator to 0, and we can find the value of z such that cos z equal to 0. So it implies that z equal to 2n pi plus or minus pi by 2, because we know that cos pi by 2 equal to 0, cos minus pi by 2 equal to 0, and also cos 2n pi plus or minus pi by 2 means 2n pi means that will complete a rotation. So after complete of one revolution again it will start from 0. So therefore here these all values of z will give the cos z is equal to 0. So therefore these are all the simple poles of the given function f of z equal to tan z. The next example is f of z equal to 1 divided by z into 1 minus z square. So here again equating the denominator to 0 to finding the poles of the function. So that is z into 1 minus z square equal to 0. So now it gives z equal to 0 and 1 minus z square equal to 0. So by solving 1 minus z square equal to 0, we can write z square equal to 1, then z equal to plus or minus 1. So therefore z equal to 0, 1, minus 1 are simple poles, because all of them are having the powers equal to 1. So hence they are called as simple poles of the given function. The next function is f of z equal to sin z divided by z minus pi whole square. So here sin z and z minus pi equal to 0. So here equating z minus pi whole square equal to 0. So it implies z minus pi equal to 0, right? And z equal to pi. So here z equal to pi is a pole, but not it is a simple pole, because the order of z minus pi is equal to 2. So it implies that z equal to pi is a pole of order 2. So therefore here z is equal to pi is a pole of order 2, right? So it is the pole. Next example, find the zeros and poles of the function f of z equal to z plus 1 whole square divided by z square plus 1 whole square. So therefore here f of z equal to z plus 1 whole square divided by z square plus 1 whole square. To find the zeros of the function, we need to equate numerator to 0, and to find the poles, we need to equate the denominator to 0. So therefore here z plus 1 whole square equal to 0. It implies that z plus 1 equal to 0, and this is equal to minus 1. That z equal to minus 1. And the order of that z plus 1 is 2. So therefore here z equal to minus 1 is a 0 of order 2. The 0 of order 2, since the power of z plus 1 is equal to 2. And next, to find the poles, we need to equate z square plus 1 whole square to 0. It implies z square plus 1 equal to 0. And we know that z square plus 1 can be written as z plus I into z minus I is equal to 0. So therefore z plus I equal to 0 and z minus I equal to 0. Here z equal to minus I and z equal to plus I. So therefore these two are the poles of order 2, because the power of z square plus 1 is 2. So therefore here z equal to minus I and plus I are poles of order 2. So therefore this is about zeros and poles of the function f of z equal to z plus 1 divided by z square plus 1 whole square. Next example, f of z equal to 1 divided by sin z minus cos z, and we need to find the poles of this function. So here by equating the denominator to 0, we get sin z equal to cos z or tan z equal to 1. So we need to find the value of z such that the tan of that angle is equal to 1. So we know that if z equal to pi by 4, then we can get tan z equal to pi by 4. So we need to write the solution in general as n pi plus or minus pi by 4. Since the tan is positive in first and third quadrant, we can write that as n pi plus or minus pi by 4, because If we put n equal to 1, that will be the pi. Pi means the second quadrant. Pi plus theta means that will come in the third quadrant, and in that quadrant tan is positive. So therefore tan of pi plus pi by 4 is 1. Tan of 2 pi plus pi by 4, tan of 3 pi plus pi by 4, 4 pi plus pi by 4, and so on. So therefore here n is any integer, so it will give the value or pole which is a simple pole, because the power of sin z minus cos z is 1. So hence z equal to n pi plus or minus pi by 4 is the simple pole, or simply we can write z equal to pi by 4 is a simple pole. And then the next example, f of z equal to 1 divided by 1 minus e power z. So here by equating the denominator, e power z equal to 0, it implies that e power z equal to 1. So here this z can be written as z equal to e 2n pi I, because we know that e power I theta is equal to cos theta plus I sin theta. So here e power I theta is equal to cos theta plus I sin theta. So therefore e power 2n pi I is equal to cos 2n pi plus I sin 2n pi. And we know that cos 2n pi is equal to 1 plus I into sin 2n pi is 0, which is equal to 1. So therefore that z equal to 2n pi I is the pole of the function e power z equal to 1, where n takes the values from 0 to infinity, means any integer. So here n belongs to the set of integers, not this z. This z is different. Otherwise you can write I, that is set of integers. And let us consider the one more example, that is e power z divided by z minus 1 whole power 4. So here we need to find poles of the function. We need to find the poles of the function e power z divided by z minus 1 whole power 4. We can directly tell that if we equate z minus 1 equal to 0, we'll get z equal to 1, and the power of that factor is equal to 4. It implies that z equal to 1 is a pole of order 2. So therefore these are some examples on finding the poles and zeros of the functions given.